So before we talk about other ways that we can use these curved arrow mechanisms, one thing that we want to recall from our general chemistry course is acid and base strength. So how do we measure that? And we really have two ways that we can follow the measurement of acid-base strength. One is the quantitative method. That's basically using pKa's or Ka's, if you recall from previously. But in organic chemistry, we're going to find a lot of times where we don't have exactly the pKa from a book on hand. Instead, we want to be able to tell just by looking at the structure of the molecule by doing qualitative strength analysis. This is going to be the more useful in general way. But real quick, we're going to review quantitative first before we go into depth on how we determine qualitative acid-base strength. So you may recall the way that we quantify acidity is we start by looking at the acid dissociation reaction for the acid. So here our acid is HA. It dissociates into the conjugate base A minus and the hydronium ion H3O plus. The Ka is the acid dissociation constant. Well, that's just the equilibrium constant from this reaction. And that would be equal to the hydronium ion concentration times the concentration of the conjugate base divided by the concentration of the acid at equilibrium. So as like a thought exercise, think to yourself, like if the acid is strong, will the Ka be bigger than 1 or smaller than 1? So try to think it through. And of course, the stronger the acid is going to be, the more the products will be favored at equilibrium. In other words, we're going to have more on the right-hand side of the equation than on the left-hand side of the equation. So translating that into the Ka equation here, we would expect these numbers, the hydronium ion and conjugate base, to be higher than the weak acid that's left behind. So that would mean that the Ka should be bigger than 1 in that case, if it's strong. And then the opposite would be true if it's weak. If it's a weak acid, we expect the position of equilibrium to be on the left or with the reactants. So the Ka value, that is one way that you can quantify acidity, but they have a pretty wide range, anywhere from 10 to the negative 50th to 10 to the 10th of the strongest ones. So instead what we do is we use the pKa, and you may recall the pKa, P of course means negative log. It's an old way to describe that function. So it's the negative log of the Ka. And basically what it is, it's just a logarithmic scale to help us measure these. So if the Ka values range from negative 50 to 10, and that means that pKa values will range from negative 10 to 50. And the lower the number, so the more negative it is, the stronger the acid is going to be. So negative 10 is a stronger acid than negative 9. 0 is 10 to the 0 would be stronger than 1, et cetera, et cetera, et cetera. So the lower that pKa is, the stronger the acid is going to be. So here's just a table of a few. This is from your book, table 3.1. And it gives us just a handful of acids that will come in useful. So we start with the strongest acid, really, which is sulfuric acid. It has a pKa of negative 9, around negative 9. Then looking here, we can imagine this is acetone. Acetone can be protonated, but it's a very strong acid if it is. So keep in mind, so we're kind of following the acidity here. This is the strongest acid up here. The stronger the acid is, the weaker the conjugate base is going to be. Sulfuric acid is such a strong acid that its conjugate base is going to be extremely unlikely to pick up a proton. So it's a very weak base. The other thing to point out here is that this is a logarithmic scale. The pKa scale is logarithmic. So for example, sulfuric acid has a pKa of negative 9. Hydrochloric acid has a pKa of negative 7. That actually means that sulfuric acid is 10 to the second times stronger, because that's the difference. Negative 7 to negative 9 is 2. So 10 to the 2 times stronger. In other words, it's 100 times stronger. So we just want to keep that in mind. Now, obviously, you'll have access to this pKa table on the test. So just keep in mind, on the test, I may ask you to quantify or to use the quantitative method to determine the acidity of a compound. In that case, you would want to use the pKa. If I say the qualitative method, that's what we're going to talk about later with the ARIO method. So we'll cover that in a little bit here. Yeah, so, and again, this is just what I mentioned on the previous slide. The stronger the acid is, the weaker its conjugate base is going to be. So just keep that in mind. Okay, so go ahead, using pKa's, do sample exercise number 3 and number 4, identify the more acidic or more basic compound based on those pKa values. Again, we're going to have this in a separate video where we kind of do all these sample problems together, and you can follow along there. If not, I recommend pause the video, figure that out, and then we'll cover those together with my document camera in the other room. Okay. So that's one thing. So that tells us the strength of the acid, but really the more important thing is kind of predicting the position of equilibrium using pKa. So basically, if we know the pKa for the acid and the conjugate acid, we can actually predict which direction the position of equilibrium will favor. So in this case, we have water as an acid and then tert-butanol as our conjugate acid. We can actually look up the pKa's for both of those. For water, it's 15.7, so very close to 16. For T-butanol, that's 18. Now, the way that we can remember this is that equilibrium is always going to favor the weaker acid and the weaker base. So the higher the pKa is, the weaker the acid is going to be. So that tells us that since T-butanol has a higher pKa, the position of equilibrium is going to favor the products, the side that has the higher pKa. Just keep in mind, basically, when we say like a stronger acid or a stronger base, think of those as like less stable forms, right? A strong acid wants to give up its proton. Strong base wants to take a proton. So the more likely it is to give up its proton, the less likely that is to be a stable compound. So that's why the weaker acid is going to be favored. Okay, and you can also actually figure out roughly the equilibrium constant, or at least the power of the equilibrium constant. The bigger the difference in pKa's, the stronger the equilibrium is going to be favored one way or another. So for example, here we have a carbanion picking up a proton from water. Water is acting as the acid and it has a pKa of 15.7 to form an alkane. Well, the alkane has a pKa of 50. That's an extremely high pKa. It's a very, very weak acid. Doesn't want to give up that proton at all. So naturally at equilibrium, we know that it's going to favor the products. Not only that, you can actually kind of estimate 50 minus 16 comes out to 34. So we actually understand that there's 10 to the 34th more products than reactants. And yeah, in this case, because that's such a huge difference in terms of the equilibrium constant for the reaction, it's essentially an irreversible reaction. The reverse reaction does not occur on an appreciable time scale. Okay, so go ahead, sample exercise number 5. This is where you're going to use the pKa's and tell me which side of the reaction is favored. And again, we'll cover this in a separate video. Okay, so we did quantitative acid strength. Now we want to actually cover qualitative acid-base strength as well. So there's one real rule, and then there's kind of several ways that we're going to evaluate this rule. The rule basically is the stronger the acid is, the more stable its conjugate base is. In other words, the stronger the acid, the weaker of a base that conjugate base is. So what we're actually going to do is we're going to focus on the conjugate base. So kind of following through here to do this qualitative acidity, when an acid loses a proton, it forms the conjugate base, you know that, and that has a lone pair of electrons that was from whatever atom was bonded to the hydrogen, that picked up a lone pair. So we're going to focus on that lone pair. Always think in your head, okay, which was the lone pair that resulted from this acid-base reaction? To figure out the stability of that conjugate base, that's the lone pair that we're going to look at. And we have what's called the ARIO method to help us determine it. So the more effectively that conjugate base can stabilize the lone pair, basically the weaker of a base it's going to be. And so that means it's coming from a stronger acid. And here we have 4 different rules. And something to keep in mind is these are hierarchical rules. So the first thing that we look at is the type of atom that carries the charge. That's the first thing we're going to look at. If there's different types of atoms on both acids, then we can evaluate it using that. We don't need to look at that. Now, on the other hand, if both lone pairs, so we're comparing two acids trying to figure out which one's stronger, if both end up being on the same atom, they both are on an oxygen atom, then we look at number two. Number two is resonance. So we're going to look for resonance of that lone pair. Basically, the ability of a lone pair to have another resonance structure, it's going to spread it out over more atoms, and so it's going to be a more stable conjugate base. Next up, we have induction. We'll talk about the inductive effect. So in other words, if both lone pairs are on the same atom, they have the same amount of resonance, then we're going to look at inductive effects next. I'll define that for you. That's the presence of electronegative atoms. And then if that fails, everything is the same so far. We get to the fourth step, which is the type of orbital, where the charge resides. And that's where we're going to evaluate, is this in an sp3, sp2, or sp orbital? So again, the way that you remember this is what I've said already. This is the ARIO method. And just remember, A comes before R, comes before I, comes before O. It has to be hierarchical in that way. Okay, starting from A, the atom that carries the charge. So if we evaluate the acidity of butane versus the acidity of propanol, the first thing that we're going to do is, remember, we're not focused on the acid itself. Instead, what we want to look at is the conjugate base. So here, if butane gives up its proton, it's going to have a lone pair on the carbon atom. And here, I can actually annotate this to make it more clear. Let's draw this out. So we're breaking this carbon-hydrogen bond, and then that's going to actually form a lone pair, like what we see down here on the conjugate base. And this should be a negative sign. That didn't transfer through. Apologies for that. Same thing here for propanol. It gives up its proton, so some base takes it away. So here we can just kind of like follow through. Whatever base, doesn't have to be anything, that's going to pick up the proton. Same thing over here, picks up the proton. This OH bond breaks, that puts a lone pair on oxygen. So that gives us the difference, and then a negative formal charge as well. So here we have a lone pair on carbon. Here we have a lone pair on oxygen. So these are the two differences. Now we notice right away, oh, they're on different types of atoms. So we're going to use this atom to figure out which one it's going to be. Now there's two separate sub-rules. Sorry, I know this is a lot of rules, but it's going to make sense here in a minute. There's two separate sub-rules for this type of atom thing. Number one is the larger the atom, the more stable the negative charge is going to be. So size becomes the most important factor. Now, if you have two atoms that are different from each other, but they're in the same period, they're effectively the same size. So this is more like what we're talking about, the difference between an oxygen lone pair and a sulfur lone pair, let's say. Sulfur is in the same group as oxygen, but it's one period below. That means it's accessing the next energy level, and so it's going to be a bigger atom. Because it's a bigger atom, it's more able to stabilize the negative charge. So in that case, the sulfur is going to be the stronger acid because it's stabilized the negative charge of the lone pair better. Now in this case, we have carbon and oxygen. Those are in the same period. So it's no longer about the size of the atom. It's actually about which one is more electronegative. So the more electronegative atom better stabilizes the negative charge. In this case, carbon versus oxygen. Oxygen is more electronegative than carbon. So that means that this is the more stable conjugate base and thus the more acidic compound. So remember, we're kind of doing two separate evaluations. Which one is the more stable conjugate base? Then once we know that, then we're ready to say which one is more acidic originally. So yeah, so again, the less stable one is the carbanion that forms butane. That means the butane is less acidic than propanol. This oxygen lone pair is more stable, so that means that the compound it came from, propanol, is more acidic. Okay, so here's an example. Figure out which of these protons is most acidic and explain why. So let's go ahead and give it a shot. Go ahead, pause the recording here, and then once you pick it up, we'll go ahead and figure out which one is more acidic. Okay, so evaluating which of these is going to be the more acidic proton between 1 and 2, what you have to do is you have to imagine what's going to be the conjugate base if either of these happen. So let's go ahead and start with proton number 1. So we just have our magical base come in here, picks up this proton, the sulfur hydrogen bond, that becomes a lone pair on sulfur. So we're just going to kind of follow it down here. That's what I'm kind of pointing out. Okay, drawing a hexagon, annotated. There we go. This one hasn't changed, it's OH on this side. But now we have sulfur, and this sulfur has an extra lone pair now. So looks like that, and a negative formal charge. Now here, let me change the color of this pen, and then we imagine kind of the same thing happening, but to proton number 2. So the base comes in, picks off the proton, and that gives us the oxygen-hydrogen bond becoming a lone pair on the oxygen. So kind of following through. There we go. SH this time. And then we have an extra lone pair on the oxygen and the negative formal charge on the oxygen. And then this circle just means a benzene ring. Don't worry about that. It's just, we'll get to that later. So now what we do is we're going to evaluate the strength, the stability of the lone pairs. So proton 2 has its lone pair on oxygen. Proton 1 has its lone pair on sulfur. So remember, that's a different atom. So we know right away we're starting with the atom rule. Then the atom rule has 2 subrules, and that's hierarchical as well. So the number 1 is the size of the atom matters. So the bigger the atom, the more stable the lone pair is going to be. So evaluating between sulfur and oxygen, sulfur is below oxygen on the periodic table. This is the bigger atom. So it's sulfur is bigger. And so since sulfur is bigger, its lone pair is more stable. If it's more stable, that means that as a conjugate base, it's a weaker conjugate base. And we know already that the one that's going to be the weaker conjugate base, that's going to be the more acidic proton. So in this case, we're evaluating the SH bond here versus the OH bond here. We form a more stable lone pair on the sulfur. That means that 1 is going to be more acidic. So kind of following through here, this is our answer. Okay, so let's go ahead and carry on. Next up, so R stands for resonance. So remember that resonance is going to stabilize a lone pair because it spreads it out across multiple atoms. This is what we talked about in chapter 2 with the different forms of resonance. By spreading out these electrons over multiple nuclei, they become more stable. So for example, if we take a look at ethanol versus acetic acid, these are both acidic compounds. They have protons that they can donate. However, one is going to be much more acidic than the other. So the way that we can kind of figure it out is, well, okay, what's the conjugate base going to look like? Here, we are going to have ethanol that is going to have its OH proton picked off. That leaves a lone pair on the oxygen, so a lone pair on oxygen. And then over here, an acetic acid, again, has an OH bond. That's going to also leave a lone pair on oxygen. So right away, we know that the lone pairs of the conjugate bases are both on the same type of atom. They're both on oxygen. So that means that A is out the window. Next up, we're going to look for resonance in the conjugate base. So let's go ahead and do that. So when we look at the conjugate base of ethanol, that's what's called the ethoxide ion, versus acetate, that's the conjugate base of acetic acid, we note that for ethoxide, there's no stabilization via resonance. There's no way for these electrons to go. There's no pi bond that it can donate into. On the other hand, in acetic acid, this lone pair is actually in an allylic position. Like, look, we have a carbon-oxygen pi bond here, and then this oxygen with the lone pair is in the allylic position, as I mentioned. So we can do our resonance where this lone pair forms a new carbon-oxygen pi bond. The original carbon-oxygen pi bond becomes a lone pair on the other oxygen. So here, this negative charge is delocalized between the two different oxygens. Since it's stabilized by resonance, that actually means that it's a more stable conjugate base. And so as a more stable conjugate base, that means that its acid is more acidic. So acetic acid is more acidic than ethanol. Now, go ahead and practice by doing this one here. We're going to pick up this practice in the sample exercise video when I'm using my document camera to show you how to do that. So go ahead, pause the video, give it a shot, and we'll pick that up in the sample exercise video. Okay, now there's also cases where we have the same amount of resonance, yet we can have differences in acidity by what's called induction. Now this might be a new word to you, induction, but it basically is, what we're saying is we can stabilize the negative charge by nearby electronegative atoms withdrawing electron density from the surrounding atoms. So what we're looking for here is, when we look at induction, we're asking ourselves, which lone pair has more electronegative atoms around it, pulling away those negative charges. And the more those are stabilized through induction, the more acidic the compound is going to be. So the comparison here is between acetic acid and trichloroacetic acid. Acetic acid, as we mentioned, it has resonance stabilization because it forms an allylic lone pair on its oxygen. Trichloroacetic acid is the same. It also forms resonance because, as you can see, this oxygen is in an allylic position to the carbon-oxygen pi bond. What makes them different then is the presence of, in trichloroacetic acid, 3 chlorine atoms. Chlorine is electronegative. That means it's going to pull negative charges. Those chlorine atoms are going to pull negative charges away from the lone pair. And as it does so, it reduces that partial negative charge. And again, the lower we make that partial negative charge, the more stable that negative charge is going to be. So the presence of these 3 chlorine atoms actually stabilizes the conjugate base and thus makes trichloroacetic acid more acidic. You can see here just comparing acetic acid versus chloroacetic acid versus dichloroacetic acid versus trichloroacetic acid. Each chlorine that you add decreases the pKa by 1 to 2 pKa units. So the more electron withdrawing groups that you have, the more stable the conjugate base is going to be. And the other thing you have to keep in mind is the closer that electron withdrawing group is, the more stable the conjugate base is as well. So the closer that it is and the more electron withdrawing groups you have, the more stable that conjugate base will be. So go ahead. Now we have 2 different protons here. We have one on the left side, one on the right side. Go ahead and try to figure out which of these is going to be more acidic. Give it a shot, and we'll pick this up in the sample exercise video again. Okay, finally. Now we're at the end of ARIO, we're at the O. O stands for orbital. So when we're trying to get this qualitative acidity figured out, the type of orbital is also going to affect the strength of the acid. And the reason for that is that there's a difference in the distance electrons are held from the nucleus in an sp3 versus an sp2 versus an sp orbital. S orbitals hold electrons very close to the nucleus. I mean, they're in a sphere, right? So that's really as close as you can get. Whereas p orbitals tend to hold electrons farther out. So the more p character that you have in your hybridized orbital, the farther away those electrons are going to be from the nucleus. And the nucleus is a positive charge. That's a stabilizing effect on a set of electrons. So sp3 electrons are farther out from the nucleus and thus are less stable than sp2, and for the same reason, sp2 is less stable than sp. Okay, so for example, like if we were to compare, here we have an alkene, so it's a sp2 hybridized carbon that has a proton on it, and here we have an sp hybridized carbon on it. Here we're evaluating which lone pair is more stable. Is it the lone pair on the sp2 orbital versus the lone pair on the sp orbital? Well, sp2 has more p character than sp orbitals. Therefore, these electrons are farther from the nucleus and thus are less stable. And remember, the more stable the conjugate base is, the more acidic the acid is going to be. So that tells us that this sp carbon is more acidic than the sp2 carbon. And that makes sense. We can actually see that if we look at alkanes versus alkenes versus alkynes. Those are all words that are going to make sense here very soon. But if you look at the pKa of ethane, pKa is 50. It's extremely not acidic. Ethylene at 44, also very not acidic. On the other hand, acetylene, that's an alkyne, this actually has a pKa of 25, which can be appreciably deprotonated. Okay, so go ahead and figure out which of these four protons is going to be the most acidic based on what you know. So give that a shot, and again, we're going to cover this when we do the sample exercise video together. So there you go. Now, one thing we want to keep in mind is that this ARIO method isn't a silver bullet. It's more like when we're looking at reactions as chemists, we want to be able to quickly identify what's going to be the stronger base or the stronger acid that's more likely to give up a proton, what's likely to be protonated as a base. And so we use ARIO to help us evaluate it. But it's not always totally reliable. There are exceptions to it. For example, we have okay, so I guess I already told this one to you, so this is not really a surprise to you, but here if you look at ethanol versus propylene, so we have the pKa's for ethanol at 16, for propylene at 43. These are different atoms, so we know that according to type of atom, the lone pair on oxygen should be more stable than the lone pair on carbon. But according to resonance, the propylene has a resonance stabilized carbocation, or carbanion, excuse me. So according to resonance, that would be more stable. Now I already told you, because I don't like lying to you up front, I want to tell you right away, the atom is more important, right? This is a hierarchical set of rules. Atom comes first. So here you already know, hey, the atom is different, so that's what's going to drive my decision. So in this case, we want to keep in mind ARIO is in terms of order. That's not really that weird. Now there is actually a different, so sometimes we do have a failure of priorities here. And the most important one is basically NH2 minus. So here, for example, what we have is we have acetylene, that's an alkyne. We were just looking at this, reacting with NH2 minus to form its conjugate base where it has a lone pair on the sp orbital and ammonia. Now here we actually do have a conflict because if we just use the ARIO method, we can see right away, oh, we have a carbon lone pair and here we have a nitrogen lone pair. We said that those are different atoms, so the more electronegative atom within the same period should be more stable. But that's not actually the case. This NH2 minus anion is actually much more basic than we predict, and this sp hybridized carbanion is going to be a little bit more stable than what we predict. So here the position of equilibrium actually lies to the right. Now we can figure that out with pKa's. So sometimes we do need to know pKa's to figure it out. Again, ARIO method just sort of gives us a set of guidelines to point us in the correct direction. Okay, so with that, let's go ahead and pick up with sample exercise number 7. You can move to the sample exercise video when you're done, and you'll figure out which of these protons is the most acidic, and more importantly, explain why using your own words. Okay, so remember, this is kind of summing up everything. We predict equilibrium position. We have two separate ways that we can figure it out. We can either determine using the pKa values of HA versus HB, so the acid versus the conjugate acid. Whichever one has the higher pKa will be favored. Or what we can do is we can figure out the relative stability of the bases, so the base or the conjugate base. And what we know is the more stable conjugate base is going to be favored at equilibrium. Now, another thing that we have to figure out is using an appropriate reagent. Now, in this case, we're going to talk a lot about that in the next lecture, which is about leveling or solvent effects. If you want to figure out, in this case, we have the acetylene carbanion, and we want to protonate it, well, then you need to use something that is able to transfer a proton to this orbital here and form the CH bond. So for example, you couldn't use butane, which has a pKa of 50, to protonate acetylene, which has a pKa of 25. So keep that in mind as you're kind of looking through it here. All right, so given all of that, go ahead and figure out, is H2O possible, a suitable reagent to protonate each of these compounds? So here what we have is we have phenoxide, then we have hydrogen sulfate, and then finally we have an ammonia, an amine anion. So go ahead and ask yourself, is H2O suitable to protonate the following compounds? And make sure to use your pKa's to figure that out. Okay, we're going to cover this in the sample exercise video. So go ahead, take a pause, figure this out, and then you can look at the sample exercise key that I've posted on Canvas. And that will do for this lecture. We'll talk about solvent and leveling effects in the next one.